Hello, science enthusiasts. Brett Burkett here from Blackland Geology and Reptiles, and I wanted to continue our discussion on climate change by looking at the modern changes. The changes that have happened in the last 70 years that we did not see on the diagrams before present the last time, to see whether those changes are outside of the norm and compare them to the full picture, and I will show you the diagram going back for 800,000 years. So today what we're going to look at are the various gases that contribute to climate change, how those gases have different residence times and different influences on the climate change that we see, what's going on, look at more recent data, understand, of course, more graphs, because graphs are complex and they need to be addressed, and then look at some of the changes that are predicted by climate change and some of the stuff that we may actually be seeing, using one example that I just saw recently when I was in Alaska. So again, a busy diagram, estimates of carbon dioxide in the atmosphere. Again, this diagram has present at 1950, and then we've added the extra portion after 1950. So why 1950? Last time we talked about this. Following 1950, we did enough atmospheric nuclear testing that a lot of the isotopes that we use to actually measure chemical changes in our environment are now influenced or affected. The proportions of them are affected by the atmospheric nuclear testing. So one of the things that we do is we say 1950 is a good zero mark, because at least before then, they wouldn't have been influenced by man interfering with the isotopic ratios in the atmosphere. So we have the dashed line on there. The dashed line represents carbon dioxide concentration at the 1950 level, right around 300 parts per million. And if you look at the left-hand axis, the y-axis there, 160 to 480 parts per million. So now that we see the full picture going back 800,000 years, we see again, roughly every 100,000 years, we have a spike in carbon dioxide. And if I would put it on the temperature, we would have a concomitant increase in temperature. Now, if you notice though, let's go back almost 800,000 years, and you see the spike there, which goes to 260 parts per million. Every time that we get a spike, roughly every 100,000 years, it isn't the same level. 780,000 years, whatever that is, we got a spike that went to 260. Then around 700,000 years, the spike was 240, 600,000 years, it was 260 again, and so on. The spikes generally vary between 240 and 300 parts per million, which is, what would that be? Something like 1/4, right? So they vary on the order of about 20%, 20 to 25%, right? I can math. And the other thing that we see here is this. If we look from 800,000 years until 1950, the biggest spike that we would see is somewhere around 340,000 years ago. If we wanted to do a very crude comparison, we could draw a line between the peak of 780,000 and the peak of 340,000, and what we'd see is a general increase in carbon dioxide peaks. What does that mean? Roughly every 100,000 years, we get a peak in carbon dioxide concentration. We talked about why that was last time. But the peaks seem to generally, really crudely, be increasing from 780,000 to 340,000 years ago. So what we could do, follow the arrow, we could draw a line that goes from there to there. But since 340,000 years, we could argue, and I think it would be wrong for us to argue that it is slightly decreasing, but basically the variation is roughly flat. So yes, we do get some lows, but then we get some highs, right? So 340,000, 1950, roughly the same height, and then we get some dips in there, but you couldn't really make a case that it is decreasing. It seems to be increasing up to 340,000 and then sort of flat beyond. What might that be? Those might be even longer term planetary changes, which are causing, say, a general increase in carbon dioxide and then a flattening. We would want to prove that, whether we are seeing a general increase and then not, we'd want an even greater time window, say millions of years, to be able to actually compare that. And the data isn't really that granular. We can't really see at that level to really get that sense to draw nice lines in there, because then the more data we have, good, but the farther back the data is more inaccurate. So crudely, we could say at the very least over 800,000 years, we may have had a slight increasing trend in the peaks, or generally flat. But who cares? Since 1950, when we can add in our direct measurements, so for the last 70 years, we have seen a spike in carbon dioxide concentration, so that now we're sitting at between 400 and 420 parts per million carbon dioxide in the atmosphere. So we have now something which has not been seen in the last 800,000 years. That would suggest one of two things. Either nature is doing something weird, or we are doing something weird. Because if it isn't nature, it's us, right? So we need to look at that, because we are seeing a spike. Now, you could say, wait a minute. We are taking direct measurements of carbon dioxide concentrations in the atmosphere now, but everything before this was those little ice bubbles that you found in the ice, right? We had the smelly ice in the fridge, so we knew that something was trapped in the bubbles. So then we stick in the equivalent of a needle and we harvest the gas. Well, there could be errors associated with that that could greatly skew the data so that our direct measurements and those bubble measurements aren't comparable. And that's a valid criticism. That's a question that needs to be addressed. For example, if we are off in the past, 20, 30% that we are off in the past, maybe the peak 780,000 years ago was much higher than we have it recorded on this graph. Maybe the peak at 340,000 years ago was easily as high as what we have today. Let's say that we want to make that as a case. If you look at that, look at the 780,000 peak. That is 260 parts per million. Today, let's just roughly say 400 parts per million is what we got. That is a 50% difference, or 53% difference between then and now. So we would have to have massive errors across all of that data to say that the data that we have obtained in the past is so error-ridden, we can't say that today is unusual. Does that make sense? So if the data was error-ridden, we would expect a much more wide scribbling, like a very bad EKG, right? But what we see is that we have variation, local variation, peaks and valleys, every 100,000 years we get a spike and then it decreases. But we would have to have systematic error of greater than 50% to say that what we are experiencing today is not out of the ordinary. So it is more logical to say that what we have seen in the last 70, 100, 150 years in that data is out of the ordinary for the last 800,000 years. Does that make sense? So that's either nature doing it or it's we're doing it. So let's talk about that. But let's go back and talk about why this gas, carbon dioxide. There are a number of greenhouse gases, specifically gases that help keep the planet warm, that we need to address. Water, methane, nitrous oxide, carbon dioxide, the various fluorine compounds, which include the propellants that we phased out in the end of the 80s due to international agreement, because we realized we were destroying the ozone layer, and various particulate matter, and a few other things, but those are the big ones, right? We're going to focus on 4 of those, and the reason why we're going to focus on 4 of those is they have the most collective effect, but I'm still going to talk about the others. So, water, methane, nitrous oxide, carbon dioxide. Next to each of them is what we would call the residence time. How much time it takes for the various gases to move through various Earth systems. What does that mean? What we're saying for greenhouse gases is they have an influence on the overall temperature of the planet, because without an atmosphere, we would be warmed by the sun, but the moment the Earth rotated, the side facing away from the sun would be really cold. So we need those gases to help maintain a more moderate temperature, so that throughout the night, we don't just immediately freeze to death, and throughout the day, we don't just roast, right? So we talked about that with the Earth's heat budget. But when we talk about residence time, we're talking about the timing of their influence. What does that mean? When we have a short residence time, the effect can be profound but limited. If you have somebody that you don't like that comes over to your house, if they're there for 3 hours, it might be bad, but you can go, oh, they're going to be gone soon, right? Water has a profound influence on the heat budget of the planet, but it moves through systems so quickly that on average, we say it moves through systems on about 10 days. That's its residence time in the atmosphere. So a parcel of water moving through the cycle will move between reservoirs on the scale of about 10 days at the maximum. What does that mean? Evaporation, we get cloud formation, we get precipitation, that rains back out. So a parcel of air is moved through various systems. So its influence in the atmosphere is limited because it's removed. Wait a minute, but there are new clouds coming up. Sure, but the influence of that moving through the system, any one particular parcel doesn't stay there trapping heat. It's moving through the system. So we are getting influence and then the removal of that influence, a new influence. So what would that look like? Well, think about what we talked about with the heat budget of the planet. We get an increase in temperature throughout the day. And then as heat is bled off or is radiated back to space, we get a decrease at night, but then we never hit zero because we get the next day's influence. So there is a residence time for solar heating of the planet, right? On the scale of a day, we get that residence time in the planet. Long term, we could talk about that influence long term, but we could say, we could look at it like the residence time of the day. We get heating and then we get loss, and we get heating and then we get loss. Water is on the scale of about 10 days. That's its influence. Methane is actually about 28 times more effective at trapping heat than carbon dioxide is. And you've probably heard this, methane comes from cow farts and cow burps and incomplete combustion, breakdown of material in landfills, and that is all true. But methane will oxidize in the atmosphere and turn into carbon dioxide, so its residence time in the atmosphere as a parcel of methane, 10 years. We go, well, cows are still farting, so there's going to be methane going into the atmosphere. And I think it's funny when you can get scientists to address that topic and they go, okay, yeah, we all know that cows fart. Like, the funny thing when you can get them to like crack that veneer of stoic intellectualism, like, okay, we need to talk about this, and then what about cow fart? They're like, oh. Okay, so 10 years, and then it breaks down. We go, well, aren't we producing new? Yes, but it's not building up, because if it built up, it is being removed from the system on the scale of about 10 years. So we're reaching a level of how influential methane is because it moves up and then it's removed. And sure, we get new, but we're not just accruing methane in the atmosphere. Nitrous oxide, which comes from incomplete combustion in car exhaust, for example, and power plants, has a residence time about 120 years. It photodisassociates. The sunlight will actually break it apart and make it into molecules or molecules that do not trap heat. So it becomes not a greenhouse gas, it breaks apart. We also have bacteria that fix nitrogen from the atmosphere into fertilizers, etc. So it is removed from the system. So carbon dioxide, what's its residence time? Of course, can't be simple. It has to be complex. Carbon dioxide has a variable residence time because there are a whole bunch of different reservoirs that can uptake carbon dioxide. Plants act very fast, and they can use carbon dioxide in the process of photosynthesis on the scale of days to months. And about 30% of all carbon dioxide is moving through the plant system. Aha, you say. But I've heard people make statements that, why should we worry about carbon dioxide? Because there are a lot of plants, and plants, carbon dioxide plus plants equals good. There's still a limit. Only about 30% of carbon dioxide moves through that system. So while we could address, can't we just plant more plants? Because that would be good all around. Number one, there's a land use thing. Number two, only 30% at current moves through that system. Think about how many plants you'd actually have to plant before it would really matter. So we could have local effects, but global effects, that would be billions and billions and billions of trees, right? Carbon cycling also moves through plant litter and soils. What does that mean? Through the process of weathering, through inclusion in creating cave networks, etc., carbon dioxide moving through the subsurface About 40% of it moves through the process of weathering, and that could take months to centuries. So that's 70% of all carbon dioxide. We go centuries. Okay, well, that's good. What about the other stuff? Well, that means 30% is longer than centuries. Carbon cycling through the deep soils, so weathering in the really deep soils, weathering the moving through, being uptaken by organisms, or weathering the material at the bottoms of the oceans, that can take millennia. And 20% of the carbon moves through that system. So 1/5 of all carbon dioxide moves through that system. And then deep sea carbon sediments and the upper mantle, the actual plate tectonics, taking carbon and moving it back in, that can take tens of thousands to millions of years. So carbon dioxide, while it isn't as effective as other gases, can linger so long that the effect is tremendous. What would that be? If methane is so much worse, that might be like having a really bad day where you drink a lot. Not advocating it, but you have a bad day that you drink a lot. Assuming you survive, your next day is bad, but you recover. So we get pulses that can be bad, but usually have short-lived effects. Carbon dioxide is not as bad, but it lasts longer and moves through various systems. So its influence is felt longer, and that's why we focus on carbon dioxide. What about the fluorines? Well, through the 1980s, companies had used various aerosols and freon compounds which involved fluorine. You've probably heard of chlorofluorocarbons, or CFCs. They had two influences. One, as they made it in out of the lower section of the atmosphere, what we call the troposphere, and made it into the stratosphere, they actually broke down stratospheric ozone, which allowed ultraviolet light, normally blocked or largely blocked by ozone, to become more effective at influencing life on Earth. So we go, incidence of cancer is going to go up because UV light is only good in small doses, etc. So that was one influence. And one little dab of CFC, the chlorofluorocarbons, could have a profound influence. And we could spend some time talking about that, but basically the molecules would destabilize the ozone, turn it back into oxygen, and it could not then block UV light. Ozone can, oxygen can't. So one little dab could say break up 400 or 1,000 molecules, so it didn't take much. One molecule could destabilize that many. So a little bit had a tremendous influence. But in addition to breaking up the ozone, which is stopping UV light from coming in, it also had a profound influence in stopping heat from coming out. And they could be up to 30,000 times more effective at trapping heat than carbon dioxide. But there's very little of it, and we went, ooh, we have this hole in the ozone layer, let's start phasing them out. And so the Montreal Protocol in, I think, 1987, international agreement said, get rid of it. We have reduced the efficacy, the negative efficacy of those products. We still use CFCs, but they are about 10 to 100 times better than they used to be. They aren't great, but they're better. And particulate matter has the scale of days to weeks, because if we have, say, a belch of something out of an industrial plant and particles go out, they will settle and they will be affected by the hydrologic cycle. So this is why we focus a lot on carbon dioxide. A lot more information than you probably wanted to know. Right? Carbon dioxide, let's just look at it by itself. When I teach my students about carbon dioxide, I bring them to this diagram and I say, okay, we're going to start somewhere, because when you're trying to explain a circle and you go, let's start here, it's really useless because it's a circle. But number one, when rocks weather, the climate system and the lithosphere, the uppermost layer of the Earth, interacts. Okay? Variability in atmospheric carbon dioxide leads to corresponding variability in the rate of weathering. So let's start, let's see. Let's start, we're talking about climate warming. So what we're going to do here. When the climate warms up, weathering of rock increases. What does that mean? If you've ever gone to a cemetery and you've seen a tombstone and there's moss growing on the tombstone, if you've ever gone to see a statue that's outside and the statue doesn't look as crisp with nice and defined lines, right? The arms that are ending in flat areas, but now they're sort of like denuded and they're rounded, that's because they're weathering. And what is that? That is dissolution. We're actively dissolving the rock like we would dissolve sugar in water or salt in water. The chemical weathering is the atmosphere itself picking out individual parts, individual atoms from that material and washing them away. When the climate is warmer, weathering happens faster, okay? When it's hotter outside, the processes can happen more quickly. The chemicals are much more active because warmer things can move around faster, and so they're much more effective at breaking rock down. When that occurs, weathering reduces carbon dioxide in the atmosphere. Why? Carbon dioxide is forming this ion, and therefore carbon dioxide is being removed from the atmosphere. Well, if carbon dioxide has profound influence on keeping the planet warm, lowered carbon dioxide leads to climate cooling, because now more carbon dioxide is being taken up in weathering, less is there in the atmosphere to keep the planet warm. Lower temperatures and decreases in carbon dioxide then reduce weathering, right? We need a warmer climate to be able to have fast weathering, but the faster the weathering, the faster we pull it out, so that starts cooling everything down. Once everything cools down, it reduces the weathering rate, carbon dioxide starts to build back up. It's a thermostat in your house. The thermostat says this is the temperature of your house. It's the ambient temperature starts to warm up. That causes your house to warm up. As it warms up, it goes, danger. Your house is warmed up, and it goes, oh, I've reached the tolerance, kick on the air conditioner. Air conditioner kicks on, decreases the temperature to your preset level. When it reaches that preset level, it shuts off. Your house starts warming back up, hits the level, air conditioner comes back on, right? Carbon dioxide moving through the environment is exactly that way. The question that we have to ask is this. If you have a 2-story house and you live, for example, in the South, where it is remarkably warm, for example, Texas, Oklahoma, Louisiana, and you have an air conditioner in your house. If you have a 2-story house, you really need 2 air conditioning units, because one can't really do the job to, if your house is big enough, to handle both floors. But what if you only had one? What if one of the systems went? Then that other one has the labor to pick up the slack removed by the one. And this is the question that we have to ask. If the carbon dioxide in our environment works like a thermostat, right? Heating, cooling. What happens if we are just pumping so much heat into the environment that the air conditioner can't keep up? Some of my neighbors, springtime, it'll be end of March, beginning of April, and we'll have a few warm days. And they'll start running their air conditioner. And I'm like, oh, June, July, August comes around. If you're already running the air conditioner, there's no way it could possibly keep up, right? If it's 80 outside and you keep your house at 78, cool. If it's 110 outside and you keep your house at 78, your air conditioner has to labor a lot more in order to keep up. So let's start with the graphs. Global temperature and carbon dioxide. Always go title first. What are they trying to tell me? And if a title is created properly, it informs you what you're going to be looking at. In this case, we have 2 y-axes. On the left-hand side, global temperature in degrees Fahrenheit. On the right-hand side, carbon dioxide concentration in parts per million. The x-axis at the bottom is years. Now, if you look at this, what we have is a temperature variation. And if you say, well, what am I looking at? Bars. What are the bars? Okay, variability of global temperature. And then the average through that data. That's what we're seeing. Okay, that doesn't make a whole lot of sense. Okay, there are 2 things going on here. Temperature in the background shown in blue and red. Black line, which represents carbon dioxide concentration. We go, but there's something else going on in this image that isn't labeled. What is our sort of zero line here? Blue below and red above. This is a good question. If you look at a graph like this, you always have to ask yourself, what is it showing you? Well, that zero line there is very interesting because it represents the average temperature recorded between 1960 and 1961 and 1990. Why that particular thing? Why that particular average? Well, statistics show that if we have 30 or more data points we need in order to sort of represent a small population, in order to be able to compute a useful average, we need about 30 data points or more. So one of the things decided back in the late 1920s, early 1930s was if we are going to talk about changes in climate, what we need to look at is 30-year averages. because now we have 30 years from which to compute an average. Well, wouldn't the averages constantly change, like 1961 to 1990, 1971 to 2000? The answer is yes, those can float through the system. But if the temperature is changing and that shifts the average, all that we're doing then is showing, say, shifting the line up, and we have red, and then the amount of red decreases and the amount of blue increases. So those are variations, and what you are looking at is the raw data trying to compute the average temperature of the planet through a bunch of different sources, and that's what represents that bar. Well, wait a minute. What is the average temperature of the planet? That is a hard number to calculate, because if you think about it, we have the Sahara Desert, we have Antarctica, we have the deserts in Australia, we have the rainforests, we have the Arctic, we have England, we have New York, we have a whole bunch of different areas which we know what their climates are expected to be. Deserts dry and hot during the day and cold at night. Antarctica, cold, right? What we're attempting to do is say, can we look at the areal extent of a particular region, like the Sahara Desert, et cetera, compute an average for that, and then come up with an average of averages looking at various regions across the planet to go, if we wanted to tell somebody what the planetary average was for a 30-year period, because then we also have to do it over years, could we compute an average temperature of the planet? Yes. And it is accurate asterisk. There are some limitations to that, because if I tell you what the average temperature is of the planet, if you go out on any given day, an average takes into account an insane amount of information in order to come up with a planetary average. You're not going to experience that average. Rarely might you experience that average. So if you look here, the average temperature from the planet is like 57.7 degrees Fahrenheit, right? According to that 1961 to 1990 average. When we calculate that average, if we look at the average for any given year, there's an incredible amount of variability from that, right? Taken off of here are our confidence intervals, because that just makes it busy, and I'll show you that in the next one, because not all the data that goes into it is as accurate as others. For example, if you have a thermometer that's measuring the temperature outside every day, but you have it right next to the concrete wall of a building, then at certain times it's going to be much hotter than you would otherwise expect, because it's next to a radiative source. So when we look at all of the data, this is where it gets confusing, and you realize how daunting of a task this is. When we look at all the data, we have to look at the accuracy of the data. We have to canvas data from the entire planet. Not every area is equally covered. You're going to see much more in, say, the northeast of the United States and the plain states, but you're not going to see as many in the as much data coverage in the mountains, because people don't live there. You're not going to see as much coverage in the Sahara Desert. In sort of pockets, you'll see it. So there is an incredible amount of variability that goes into that data. But what are we trying to show here? Well, what it looks like is temperature is remarkably variable, but in general, from 1880 until 2010, in this case, what we had was an increase in temperature. It looked like we had a decrease from 1880 to about 1910, and then an increase up to about 1940, and then sure, with some variability, data was flat until about 1980, and then the temperature increased to 2010. But from 1880 to 2010, there seems to have been a temperature increase. Whew. At the same time, there is a massive increase in carbon dioxide concentration, from about 300 parts per million in 1880 to, in this case, 2010, we were up to 386, 85 parts per million. And now, adding in that last 10 years, we're up to 400 parts per million. Why don't I have that? Here's the other thing about data sets. Unless they are constantly updated, they eventually have a point where they just like, well, this is where the data pool is, right? And when you're looking at graphs, they might not have that recent period of data, or they might chop off the other end. Are they doing that to hide something? No, because data sets were created at different times, and the internet, if they've been posted there, like like something coming out of the depths of the earth. They just linger forever. So we have this. So when you're looking at a data set, you have to go, oh, what is it showing me? And look at all the parameters, which is why it's very easy to throw something up on a screen and go, the data clearly shows. Here's the other thing. Coloration. One side is blue and one side is red. Red immediately comes up with angry, love, hot. Those are the three things, right? Or stop, warning. So when we do this, when we color the data that way, then it immediately predisposes us to go, warmer on that side, colder on that side. But we have to remove that. And sometimes that's done intentionally. Other times it's just done because those are the best color scheme, right? To really show the contrast. But when we do that, we go, cold, hot. Look at carbon dioxide. It doesn't seem to follow the temperature perfectly. You see that? This region here, we have a general increasing black line, but the data is highly variable. But then as we get into the red on the right-hand side, now they seem to line up. It isn't a one-to-one relationship, it is complex. And remember what we said the last time, if we look at the really big time scale, temperature can go up, followed by carbon dioxide, because increase in temperature causes an increase in breakdown of material, right? And as that material breaks down and carbon dioxide is released, then carbon dioxide can reinforce the pre-existing temperature conditions. And in this case, temperature is variable, but carbon dioxide is increasing. What we are arguing now is that carbon dioxide may be forcing the temperature to go up. We've sort of reversed the natural scheme. Confused yet? Let's look at an even more complex data set. And this one, first of all, variations of Earth's surface temperature, departures in temperature in degrees Celsius from the 1961 to 1990 average. That's the top graph. Bottom graph, departures in temperature in degrees Celsius from the 1960, but now we're going back to the last 1,000 years, right? Top one, 140 years, bottom one, past 1,000 years. Why? Why do we do this to ourselves? Because we need to understand past history. Why do we keep changing? One goes to 1880 and one goes to 1860. The accuracy of the data at the time to create that graph, what the researchers had access to, etc. If you look at that top graph, I have stared at this top graph for the last 12 years. And as much as it is showing the information, it is problematic in the coloration for colorblind people. It, to me, looks just like oranges and reds, and it's hard to see it. So I'm going to superpose on this the same thing, just rendered in different colors. Same thing rendered in different colors, broken out by decades here, right? To give contrast, and same image, just changed. The only thing is we sort of stretched it out, right? But not even that much. We basically shifted it over. This one, both of these are the same thing, come from the Intergovernmental Panel on Climate Change, the UN working group to try and understand planetary climate change. The image here comes out of Encyclopedia Britannica, of all places, right? But let's look at what it says. Before we actually get into the text box on the left, which is going to drive you insane, let's look at what this actually says. Variations in Earth's surface temperature over the last 140 years, from 1861 to 2000. Departure in temperature, in this case in degrees Celsius, because remember we said most scientists use degrees Celsius, from the 1961 to the 1990 average. So there again, we have that 30-year floating average. So then what do we see? We see bars, like we had in the last graph. We have bars, then we have these thin little lines that look like the letter I, and then we have a line that runs through everything. So now let's look at the text box on the left. The Earth's surface temperature is shown year by year, which are the reddish bars, and approximately decade by decade, that's our solid curve. We'll come back to what it says after that. There are uncertainties in the annual data, and those are our thin lines that look like the letter I, that are the 95% confidence range, that the temperature has to be in that range, somewhere in that 95% confidence range. So what are we looking at? We are looking at Earth's surface temperature, yearly surface temperature, and then the decade average, if we would average it by the decade, and then the confidence that in any particular year the temperature is in a particular range. Okay? What does that mean? Well, now let's look at what the actual curve represents. It says a solid curve, a filtered annual curve suppressing fluctuations below near decadal timescales. That's not code, but it's the scientific lingo that says this. There's so much variability, and there are so many short-lived events that can have a profound influence on the temperature, like El Nino and La Nina, and whatever is causing the Saharan dust to come over to us. And there are a whole bunch of variations that can happen that can be short-lived, acute temperature fluctuations or influences on temperature that we look at those, we look at them in context, and then we sort of filter out some of those to see what the influence would be even without those profound changes. The uncertainties. Why are there uncertainties? There are data gaps we might not have had because, for example, during World War II, we might not have had global coverage. Makes sense that we wouldn't. We had other priorities, random instrumental errors, and uncertainties. For example, people that have their thermometers next to concrete buildings, etc. Uncertain and bias corrections, when uncertainties and bias corrections. So when we're attempting to filter out some of those extreme short-lived changes, there are uncertainties in our ability to do that. In the ocean surface temperature data, because we also have floating sensors and other sensors that we have to actually measure temperature data, and there's biases in those, there's errors in those, and adjustments for urbanization over the land. Because if I urbanize a particular region, that can influence the local temperature because more concrete, more sunlight reflected, more asphalt, more heat trapped. If you say, I feel lost, I understand. This is why when somebody throws up the data and they go, the data clearly shows the temperature has been increasing over the last 140 years, it's our fault. There's two things that happen. Well, yeah, okay, I don't understand enough about what's going on about statistics or whatnot to really understand, or you're just trying to lie to me because I don't know what's going on. So we need to look at what's going on here. What we see here, again, there's that average. Here it's not colored red and blue, but what we see is a general increase in temperature from about -4 degrees Celsius, which was below the average, to about 0.4 degrees Celsius above the average. That comes out to be about 1.5 degrees Fahrenheit increase of the average temperature of the planet. And if you say 1.5 degrees, that's not problematic. It could be, because if your body temperature, the human body temperature, increases by 1.5 degrees, you now have a fever. And the manifestation of that fever are alternating sweats and chills. So what we could be looking at is a planet that has a fever that is undergoing alternating sweats and chills, essentially destabilized climate. So what we expect and what we are used to might be being off. We have those years of like, it was never this cold. Or what we are getting are more extremes than it never used to be this dry. It was dry, but never that dry. Okay, let's look at the bottom one. The bottom one includes what we call proxy data. A proxy is something that stands in for something else. So what does that mean? If we look at tree rings, we cut a log and we look at the rings on the tree, we know that every year the sapwood, the actual growing wood adds a new layer to the tree, right? And there is some truth to the idea that the variation in thickness has to do with the environmental conditions. If we get a drought, it might be shorter. If we get more sunlight or more moisture, it might be wider, right, or narrow and wider. So there's variation that can happen with the scale of the tree rings. Sometimes they're wider, sometimes they're narrower. But if those are related to environmental changing conditions, we may be able to look at, say, for example, tree rings to understand temperature variations. Oh, it got really cold, it was a bad growing season, and so the tree rings might have been like this. It was really warm and it was nice, and the tree rings were a lot wider. I exaggerate, of course. That is a proxy data. We didn't sample the temperature directly, but we have something that could stand in for the data. Pollen counts. If we have really nice environmental conditions, we might get more pollen. If we get cold and miserable conditions, we might not get as much. And pollen, being that it's remarkably durable in the sediment record, going back thousands of years, because it's a nice little solid material that actually resists breakdown. There are a whole range that we could look at. We could look at sediment thicknesses in lakes that seasonally freeze. If they freeze and then they thaw, when they thaw, the water is more energetic, so the sediment tends to be granular. If they freeze and the water is more calm under the water, right? Sorry, the water is more calm under the ice. The sediment tends to be finer grained because the water is more quiet, and so stuff can settle. So we can look at alternating freeze-thaw cycles in water to understand past temperatures. The problem with that is there are errors associated with each one of those. And errors aren't necessarily a bad thing if we understand that. People go, well, there's errors in your data. Yeah, because there are variations in the sensitivity of our equipment. So this, if you look at the text box, variations of the average surface temperature of the Northern Hemisphere for the last 1,000 years, reconstructed from proxy data, calibrated against thermometer data. We understand how temperature works. We then try and calibrate that to the actual physical realities in our trees, etc. What are we looking at here? The blue curve is the yearly average. The black curve is the 50-year average. Why 50 years? Because now we're going back 1,000 years, so 50 years makes some sense. But regardless, however they average the data, they need to tell you, otherwise you don't know what you're looking at. The 95% confidence range in the annual data is represented by the gray region. So we know that it has to be somewhere in this region, right? And then if we average through that data, what we see is either a temperature decrease up until about 1850, and then a temperature increase, or functionally, because there's so much variability in the past, a flat condition, and then we get warmer. Why is there so much variability? The farther back in time we go, the less accurate we are. It's as simple as it is. It's the same thing with historical documents. The farther back in time we go, the fewer documents we have, right? Now, we've also then superposed the proxy data and then how closely they resemble the temperature data that we have. And if we do that, there's general equanimity with that, right? There's general equality. And then when we do this, these proxy data. It takes some time for trees to accumulate and for us to cut down to get any accuracy and for pollen to accumulate, et cetera. And that's why that drops off in that last little bit. Does that make sense? So, more data. Look at ice cores. We could look at ice core data because there we're getting carbon dioxide and then we're relating it to temperature. As we get in more recent years, we can then individually separate it, whereas all of this has been smoothed. This is one of those diagrams that if you don't understand, you go, well, why don't we have red dots here? Because here, the slope is steep enough that we can now see individual years, whereas we can't as easily in this time scale. But slightly problematic. But what we generally see, carbon dioxide concentration increasing in the recent years. Okay? Let's look at one more graph because clearly you haven't been killed by graphs yet. Global warming here, right? We're talking about global warming. We're going to come to that next time, and we're going to talk about what's the difference between global warming and climate change. Nothing, but why the actual words have been used. But look at what we got. Annual global surface mean temperature anomalies. Annual, yearly, global surface average temperature anomalies. So deviations from an average. What's the average? Again, I should have put it on here, but the average is again that 1961 to 1990 30-year floating average, right? On the left-hand side, degrees Celsius. On the right-hand side, degrees Fahrenheit, and three separate plots: land and ocean, ocean, land. If you look at all of those, the one that has the most variability is land. The most variability happens on land. Why? Rock, soil, easy to heat up, easy to cool down. We know this. Why? Because it traps the heat largely at the surface. If you've ever gone to the beach and you walk out onto the sand and the sand is burning hot, you go, hot, hot, hot. Dig your feet through the sand, it's cool. This is why we can bury people in the sand and they find it fun. Because it keeps the heat closest to the surface. It changes its temperature quite quickly, cools off quite quickly, and that heat is largely trapped near the surface. Water takes a lot more energy to heat up because water is so good at distributing the heat energy. This is why we say a watched pot never boils. You stick a pot on the stove, the pot itself gets physically warm, but the water inside stays cold. You can have a pot on for 5 minutes and stick your hand in the water and go, oh, it's not boiling, even though you've been fluxing heat into that water. And then the average between land and water, we're seeing it here. So if we see that, what are we looking at? Again, here's the danger. If you're trying to make a particular case, be very careful about what colors you use, because you're predisposing the audience to look at it, right? This came out from the National Oceanographic Administration, right? So what we have, blue below that 1961 average, 1961 and 1990 average, red above that. But there seems to be a flop that happens somewhere around in here, where, makes sense, if we have an average from 1961 to 1990, right? What we generally see is cooler conditions and then an increase in temperature to more modern conditions. Why do we always start at around 1880, 1860 to 1880? If we're looking at actual direct temperature measurements, we didn't really have a global group of people collecting data until about 1880. And there were various scientific observatories across the world that were collecting data, but we didn't get really any large-scale consistency, or put it this way, enough data points until about 1880 for us to actually be able to have any sort of coverage. Before that, heck, back in as far as Aristotle, there were ways that people were like at least annotating temperature, etc. But in more recent years, since the Renaissance, people had devices that were trying to measure temperature, etc. But they were few and far between, scattered, so we didn't have the coverage necessary for that data to be really useful. We might be able to get a lot of good data for one region. We could see, say, how Venice has changed over time, but not in, say, 1720 to be able to extrapolate that to the entire planet, right? So now let's put the graphs aside and let's talk about some changes that we've seen. The 5 warmest years on record have occurred since the 5 warmest years since 1880 have occurred since 2010. The 8 months of 2016 were the warmest on record at the time that this was created. So I created this slideshow actually a couple of months ago, but it's the same. The ice loss in Antarctica has tripled in the last decade. The seasonal snowpack has decreased over the last 50 years. So for example, snowpack in the Rocky Mountains, snowpack in the Himalayas, etc. Sea level rise in the past 2 decades has doubled that of the last century. And the ocean acidification has increased 30% in the century. That is the uptake of CO2. There's more CO2 to uptake, so they are forced to uptake more CO2. And when they do that, I add CO2 to the water and it makes it slightly acidic. So the waters are getting more acidic than they have in the last century. We're seeing a rapid increase. Right? So we're starting to see in recent years, warmer, warmer, warmer. Is that a result of more testing, more analysis? Doesn't seem like it, because we have been tabulating data for the last 140 years, since 1880-ish, right? And in recent years, it seems to be accelerating. This isn't a conspiracy in this case, it's just we're looking at the data, right? So let's talk about the effects, because this is the tamale. What's happening? Could warmer conditions cause an increased growing season, right? Now we don't get the seasonal decrease that actually restricts crops growth. Yes, we could get an increased growing season, but some germination absolutely requires a cold period. My dad runs a tree nursery. And for many of the things that he wants to plant, he needs to cold stratify them. He needs to put them in a refrigerator for a period of time to simulate a winter-like environment so that they will actually germinate. If we get a longer growing season, that doesn't necessarily mean we will get more crops, because some things need that cold period in order to actually grow more robustly the next season. We need seasonal variation. If we mute that by increasing the temperature of the planet, for example, or if we make that more extreme, then the hot periods might be hotter than outside of their tolerance, and the cold periods may be too cold for that to occur, for germination to occur. The stress of changing between, or they just don't get enough germination depending on the manifestation in the region. They might not get enough variation in temperature to actually germinate. And that's one of the interesting things. People will make this statement. So the entire planet's just going to get warmer? Remember, if the analogy with the human body works, alternating sweats and chills, sweats and chills, sweats and chills. So it could make one of two things happen, and probably both. We could make more extreme seasons, or the areas that were warmer start getting colder, and the areas that were colder start getting warmer, so we just shift everything. And we could also shift it in time during the year. So what does that mean? That means that we either get more extremes in one area, or we get muted in one area and more extremes in areas that didn't have that before. So we are changing the environment. Spread of insects. If an area was at a certain elevation that would kept it at a cool temperature that, for example, prevented mosquitoes from breeding, now if it warms up, an area that did not used to experience mosquitoes might. What might that mean? An area where everybody is completely virgin to something like mosquito-borne illnesses like malaria or West Nile virus, etc. Now they're exposed to it. Spread of ticks, the spread of disease. In certain areas, certain diseases can't easily take hold because the climate itself limits that particular disease. Not necessarily anymore. Now, we go, wait a minute, won't it balance out? If we get more extremes in one area, we might get less extremes in another. That's true. But we now have potentially a virgin population which has not grown up with and developed adaptation strategies for that in their bodies themselves, so that now, yes, it is true, we might get more extremes and less extremes, but the influence on them could be dramatic. Sea level rise, we talked about that in the last slide, accelerations. Well, if we get sea level rise, doesn't sea level drop? Well, in that case, no. If we get more melting on land of ice, and that water that had been stored on land is now put into the oceans, sea level rises, and cities that are close to, or in some cases below sea level, they just can't pick up and move. I was in New Orleans a year ago, April, and it was strange being in the French Quarter, looking across the Mississippi and seeing that you're basically looking on a flat plain and you're looking at treetops because the other side is below sea level. Now, what happens if sea level rises? The effectiveness of the levees are minimized because the water level itself rises, so they're not as high above the water as they used to be. Storms. Here's one of the interesting things. To show you that there's so much variability going through the system, it's hard to make certain predictions. The National Weather Center, the National Hurricane Center, has said this. As climate warms up, the amount of precipitation in a hurricane may actually increase. In other words, more rain in the single hurricane. Wind speeds may increase, in both cases by up to 10%. Intensity may increase. What does that mean? That means if we know we categorize hurricanes from 1 to 5, we may get more on the upper end of the dial. The weird thing is we may actually get fewer weaker hurricanes. So we get potentially fewer hurricanes overall because weaker hurricanes are generally more numerous than larger hurricanes. But we may get, say we have 18 hurricanes in a season, now we might only get 10 hurricanes in the season, but proportionately, we get more 3s, 4s, and 5s. So it's a weird, and they're not generally uniform. There might be some suppression of Atlantic hurricanes and some increase in Pacific hurricanes because this is moving through an entire system. Now let's look at several for business. Movement of shellfish. Shells, the sea creatures, have calcium carbonate shells. If the oceans acidify, if the temperatures heat up, those shells are made weaker and break down and kill shellfish because they need their shells. So the shellfish spawning grounds may actually migrate. So if a boat has figured into, if it's a boating company has figured into its costs, travel out to a particular spawning ground where they harvest, now they're going to get less and they might need to go farther in order to actually access the same shellfish. So that causes costs to go up. Droughts. Let's say an area is already tenuous, like the American Southwest. Lake Mead, for example, in the Hoover Dam. We are starting to see an incredible amount of water loss in that region. Now that comes from several things: overuse, misuse and misallocation, and climate change. Overuse, the temperature in that area is great for growing, but they don't get much water. So that's why we built the Hoover Dam, to try and give them a much more uniform, stable amount of water. But there are now 7 states that depend on the Hoover Dam, and because of infighting and who gets water rights, et cetera, and burgeoning populations in Phoenix, for example, and in certain parts of California, so much water is being used that Lake Mead is dropping. And so much water is being used that it may get to a point that the intakes for water that we use for hydroelectric power may become dry. And they're talking about doing massive engineering projects to build new water intakes lower down to ensure that they always have enough water to get power. They've been fighting over the region for years, and the federal government said, you 7-state coalition, you make a decision or we will, and you won't like it. Part of the reason that that region has so many people is in part because of California, because California knew that the temperature was great, but they didn't have the water. They could grow, as long as they could get water coming from the mountains, they could grow crops because the growing season is great. And they convinced people that their crops were better than other people's. California cow is a happy cow. Our raisins are sun-made. Our oranges are sun-kissed. And I tell my students, I go, all raisins are sun-made. That's called photosynthesis. That's how it works. But they convinced people and they branded their food as better. And so now California produces 20 to 25% of the nation's food on 1% of the land. So they absolutely need water. So even if the main things are water misuse and misallocation and overuse, climate change is not going to help that. If they get more droughts, now we already know the squeezing that has happened on the farmers that are there. If they get it worse, they won't be able to exist. Extinctions. Certain animals live in such restricted environments that if the environment changes significantly, they're going to die out. Glacial loss. There are 2 types of glaciers, right? We talked about ice sheets and glaciers. So ice sheets on land. I'm going to lump ice sheets and all of the on-land glaciers together. There's also sea ice, right? Individual icebergs and sea ice. If the sea ice melts, that does have some influence, but it doesn't really have an influence on sea level because the ice is already in the glass. But the land ice, that's on land. So when that water melts from the ice and goes into the oceans, that can affect sea level. But it can also affect tourism. Over the next few slides, I'm going to talk about shellfish. I'm going to show you a graph of shellfish. I'm going to show an image with shellfish. We're going to talk about the California water wars, and then I'm going to talk about my experiences on Mendenhall Glacier this past summer, a year ago, with my wife, so that we can see the effects on glaciers. All right? So, Lake Mead. Despite signs of interstate cooperation, the decline of Lake Mead isn't near being solved. This problem, I'm not going to claim, is climate change only. It's a product largely of overuse. So many straws in one glass, climate change isn't helping. And the snowpack is declining. That's a result of climate change. If you look at this picture, what we have is a distinct, what we would call a bathtub ring. The water used to be this high. There has been a dropping of water levels. So this used to be buried underwater or submerged underwater, and now it's exposed. So it's a bathtub ring. They're getting to a point that the water level has decreased so significantly that in addition to this being a water source, it's also a power source, that the power plants might not be able to function because they're not, the intakes to the power plants aren't sufficiently deep to be able to handle the decline. And like I said, the government said, fix it or we will. So the 7 states are trying to negotiate a Southwest water pact to better handle the water. To show how significant the problem of water loss in the region is, again, overuse, misuse, and misallocation, and climate change. You might have seen in the news that certain surface lakes, surface reservoirs that California uses to supply water to its crops, they actually put these weird floating balls that look like ping pong balls across the surface of them, because the heating of them heats the top of the ping pong ball, and the heat stays close to the surface and then doesn't easily cause the water to evaporate. So they have these weird, like, we need like 800,000 ping pong balls. Why? To save our water. It's one of those things that a problem required a novel solution. But it was one of the, people started going, why do they need so many ping pong balls? Because they have a major water problem. It was the best, most logical solution for it, right? Let's talk about Mendenhall Glacier. I didn't take either of these pictures because, again, I was there in 2019. But these pictures, William Ogilvie and Gary Barash, right, 1894, 2008, taken from the exact same position. We can see here on the left, the data clearly shows, we can see here on the left how far out the ice is. On the right, the ice had retreated greatly and exposed a ridge of land and portions of other ridges that hadn't previously been exposed. And we can see this used to be just an isolated peak surrounded by ice. Now it's exposed. Why is this a problem? Mendenhall Glacier is the most visited glacier in the entire world. It's certainly the most visited glacier in America, and I'm pretty sure my statement it's the most in the entire world, because it's so easily accessible. And you just drive up at Juneau, and then you can take a small car out of here and then drive up and hike up to it, right? In this image, we have the Mendenhall Visitor Center, and we can see the ice. Glaciers are interesting because a glacier is a collection of ice that is so thick, usually at least 30 feet thick, that the particles, the individual ice snowflakes, have compressed down and now will deform like silly putty under the influence of gravity under their own weight. So as they move, ice is always moved from the top down toward the bottom, from the head to the toe. And this is moving like a tank tread. If I were to stick poles across here or put a building on here, then it would be shifted downward toward this lake at the bottom. Well, look at the right-hand image. In 1910, the ice was here. In 1931, the ice was here. 1948, 1962, 84, and 96 to its current level in 2005. And it has receded much farther beyond this since 2005, in the last 15 years. This visitor center was built here to be as close to the toe of the glacier as possible. Now it's retreated. So it isn't as accessible as it once was. And that could hurt, if nothing else, tourism. Does that make sense? Because think about it. We are now seeing a vanishing commodity. If you've ever seen these books, the 100 animals to see before you die, the 100 places to see before they're gone, here's an example. Because if you look, in 100 years, the ice is now basically beyond this image, right? Or at least at the edge of this image, but it's gone beyond that. So, profound influence of climate change, big scale things, diseases, etc., small scale things, tourism. So let's talk about the extremes and then I'll end this lecture. We talked about the hurricanes. Depending on where we are, they could get more intense. They could have more rain, which for something like New Orleans, we don't need another Hurricane Katrina. If there's more water, there's more flooding, there's more death. The wind speeds could increase, same problem. Where they are located, the smaller ones may decrease, so there are a few smaller ones, but the big ones are worse, right? There could be fewer Atlantic hurricanes, more Pacific ones. We shift them, but there are some influences. Snowy mountains. Well, if the planet warms up, then we get a loss of seasonal snowpack. We could run into situations where we don't get the replenishment that is necessary to keep all of our agricultural systems in place. Lake Mead drying up, for example, or at least decreasing to a point where it's dangerously low. We see this happening in the Himalayas, in Tibet and Nepal, where they depend on snowmelt. If the snow is in the mountains starts decreasing, then so many people which depend on that for water and agriculture, they lose out. Floods. If there's more water moving through the system, we can have more floods. In the case of the hurricanes, more water moving through the system, the severity of even seasonal flooding could be worse. Landslides, more water moving through the system, decreases friction in the surface of the ground. On steep slopes, it can cause failures. Debris flows. What's the difference between those? I'm going to give an entire lecture at some point on mass wasting. Landslides is when the ground is actually sliding. Debris flows are when it's moving in individual pieces. Mud flows are an example of that. Both of those, dramatic, I'm using sort of the vernacular here, but moving material, water increases the risk of that. More water, more flooding, more mobile material, more movement of material that can kill people. Frequency and strength of thunderstorms. Well, if we have a lot of heat going through the system, more evaporation puts more moisture into the atmosphere, and then all thunderstorms are changes happening within a cloud, and the more energetic it is, the more severe weather we get. And that's what we're talking about there. Using the vernacular of thunderstorms, we're really talking severe weather, right? They could become more severe. They might not be as frequent. It depends on how all of the dominoes interact with each other as they're falling. So we could get more severe thunderstorms, but the location of them, where they occur, that shifts. Or the number of them increase or decrease depending on where we live. Deserts could expand, or areas that weren't deserts could shift. So the areas along the edges of deserts, which are sort of marginal land, could become deserts. The areas that we have, like say the Sahara Desert, that could shift as a result of changing climate, because remember, alternating sweats and chills. We don't just get one extreme, we get dominoes. We could get one extreme where everything gets drier, but then some area that was dry gets wetter. Could the oceans get more salty? Well, why do we care? It's the oceans. We don't drink the salt water anyway, right? But water moving through the system, the ocean currents and the stirring of the oceans brings up nutrients, including salts, not just sodium chloride, but sodium, magnesium, other materials that we would call as sea salt, brings up nutrients that supply fish stocks that we harvest for everything from fillet of fish to what you get at the store, and the biodiversity of everything that feeds off of those. That could change depending on the changing climate. And of course, insect plagues, disease, wars. Why? Resource wars. The situation is complex. I'm not going to say that it isn't, but we could see that there could be profound influence on our current system that we depend on if the system starts to change outside of the bounds. We depend, for example, on the human body, it being roughly 98.6 degrees. We are in homeostasis. There are inputs, outputs, we get warmer, we get colder, but we have generally the idea of a day-to-day variation that we can tolerate. If it gets much out of that, either too cold or too warm, our body can't tolerate it. And that's the question we have to ask. Is this happening here? It is hard to predict all of the variation that can happen. And for every time that we could say, well, it's going to get more severe, then somebody could come along and go, well, it's going to get more benign. Depends, because remember, we could have an area that was extreme that is now, for example, Texas. You could have a section of Texas that we know is hot and dry, and now it gets a more moderate climate. We go, well, that's good. Is it? Because the local flora and fauna depend on that extreme condition, even if you don't like it. If they change, so that's one of the things that we need to investigate. So what have we done? We have talked about the basic science. We have talked about the effects of volcanoes. We have talked about modern changes, looking at a crazy amount of data. And we have seen that there can be tremendous variability. Look at it one more way. I'll end with a thought, and then I'll end the general conversations right now, and then I'll talk about where we're going to go next. If you have a system where you expect a certain growing period and crops that you have convinced the world to buy from you, right? We get peanuts from here and avocados from here, and we get certain animals that we graze here and we herd here, and we get a certain tourism that is dependent on the glaciers to exist or the forest to exist, etc. The climate change argument does not say that the entire planet will be reduced to nothing. It says that the system that we have built our society on California does this, and Texas does this, and Japan does this, and Australia does this. If that changes, think about the domino effect through the economic system, through the political system, through the people that have power and those that don't, because what we depend on varies. And that's the concern that we have. Not that we will reduce the planet to nothing. That's not the question. We have a system which is inherently, we have streamlined it, right? We have branded it. We've packaged it, we've slapped it on a lunchbox, and then we worry about the system going through. What we're going to talk about next time are politics of it. I've tried to keep those largely out of it, but we're going to look at the modern debate, the words that we use, the danger in using certain words, the politicization of it, and why that has occurred and what that means. We're going to look at how people use words, and we're going to talk about how, even though it is framed as two sides, the way that we typically frame the debate shouldn't be. It shouldn't be, because then it becomes antagonistic, us versus them. So we're going to do that. And then the last thing that we are going to look at, we've done ways that we can mitigate it, right? Or at least little things that we can do in our environment that we need to look at to discuss how we might be able to help if we think it's a problem, etc. So if you've liked this, subscribe, leave a comment if you have a question, and I hope to see you next time. Brett Burkett, Blackland Geology and Reptiles. My wife will be giving some lectures on volcanoes, on volcanic snakes, right? She's going to be giving some lectures on snakes soon, so we'll upload those. And if you have any questions, if you have anything that you're interested in, put it in the comments. If you thought that this was too wordy, remember, we don't have all the panache necessary, all of the crazy animatics and stuff. We wanted to present the science, and I hope that I've done that. If you like it, subscribe, share it with your friends, and I'll see you next time.